Oh my god, can it be true? Check it, dudes. We've actually transitioned all the way from crazy chapter 1 to creepy chapter 2. And chapter 2 is where all the magic happens. It's where we actually start doing calculus. Chapter 1 was all about making sure we had the skills necessary to go forward into this great unknown calculus world. But now we're there. We're going to hit it. We're going to do this thing called the derivative and instantaneous rate of change. You may remember concepts of rate of change from such chapters as Chapter 1, the only chapter we've done, where he talked about something like average rate of change and how you can connect 2 points and such. And here we're going to do something a little bit crazier. So as always, let's start with a motivating example. It turns out that I mutate into a werewolf and I like to nom 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 the campus bunnies. Let's make sure we know what's going on here with a little nom. And then maybe also a horrible bunny scream. Pop. And also let's make sure we know that this is a cloud and this is a moon, because my drawings are amazing. All right, so dudes, now you know the deal, the true scary nature of my hairy being. I like to mutate into a werewolf. And so the question we're all asking ourselves is this. If I know how much hair I have on my back at time t, then the real question, where the money is this guy. How fast is my back hair growing at a specific time, at time 4? So dudes, the question of how fast something is growing should make you think back to average rate of change. We talked then about how rate of change equals slope, and fast, the idea of how fast something is growing, that's just a particular kind of rate of change. Fast means rate of change with respect to time. So whenever you see fast, fast or speed or anything like that, you should think about that as a kind of rate of change. And rate of change is the same thing as slope. So if the question is how fast my back hair is growing at a certain time, what I pretty much want to do is look at this graph and figure out the slope at time 4. But that's kind of weird, right? Like when you talk about slope, that's kind of like talking about a line, and you need 2 different points to find a line, or you need 2 different points to find a slope. And here we only have 1 point. So here's the thing, dudes. We're going to get a slope based on drawing this thing called the tangent line. Tangent line. And here's the idea of the tangent line. The tangent line is always drawn on a graph, and it's a line that just barely skims across the surface of the graph without punching through it. So maybe just some quick examples of what it's not. A line that looks like that kind of punches right through the graph, so that's not what we're looking for. Even a line that looks like that kind of breaks through the graph, that's not what we're looking for. We're looking for a line that just barely grazes along the top, something like that. Now that may seem random to you, but actually here's the idea. It turns out that for any function, you can zoom way in on it. So let's pick like a certain region here. There's a region of the function, and the whole function looks curvy, obviously. But dudes, if we zoom way in this region, the more we zoom in, the more the function starts to look flat, just like a line. So if we zoom in on this puppy, all right, that's all my computer will let me do. But you can see like it's still curvy in that sort of circle region, but it's a lot less curvy than before. And you can sort of buy the idea that if we zoomed in even more, it would look even more straight. And so what the tangent line really is it's the line that you would get if you could zoom all the way in and view that piece of the function as a straight line. So it's this puppy right here. Yeah. All right. So I hope that sort of makes sense. It's a line that connects on the function just at that 1 point, skims along, going in exactly the same direction. So, oh, now I have to resize. Oh God, everything's terrible. Maybe, how's that? All right, I think that's good. So that's the idea of the tangent line. And of course, we can like extend this puppy all the way out. Doop, 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 doop. All right, that looks like a proper line. And now, dudes, here's the thing. Let's go back to what we were talking about. The question is, how fast is my back hair growing at a certain time? We know that fast or speed, those are just notions of rate of change or slope. So when you're asked a question about how fast something is changing, or what's the rate of change at an individual point, then the answer to that question is going to be the slope of the tangent line. If all you know is what happens at 1 point, the only line you can draw is the tangent line. And because we're looking for slope, then the answer is going to be this slope. And so maybe this slope is something like 0.75. Let's make that up. And if that's true, if the slope is 0.75, then my back hair is growing at a speed of 0.75. And because this is speed, we have to make up a time unit. Let's say this is hairs per minute. Does that sound good? 0.75 hairs per minute. That's actually not a whole lot of hairs. It's probably larger than that. But that's cool. That's our answer, dudes. So let's review this thing we just talked about. If you remember from chapter 1, the notion of average rate of change is, well, we usually summarize this as delta y over delta x. It's the change in the y values divided by the change in the x values. And to do this, of course, we needed 2 different points. This is the same as the slope formula. This is all chapter 1 stuff. But the stuff that's new for 2.1 is this. If we talk about rate of change at a point, and by the way, this is also known as instantaneous rate, rate of change. If we talk about rate of change at a point, which is also known as instantaneous rate of change, then that is the same thing as the slope of the tangent line. We only need 1 point for that. Well, we need 1 point. We also need to know what the function is. And that is also what is called the derivative at the point, or the derivative of the function at the point. It's called the derivative because derivative ends up having lots of properties, so that's why it has a special name anyway. We don't want to go around saying rate of change at a point, instantaneous rate of change all the time, because that's a mouthful, and people would look at us funny, and they would punch us in our noses. We don't want that. So we've got a special name for this thing. It's called the derivative, and the derivative just means the slope of the tangent line at that point. Now we'll do a few more examples in a sec, but for right now, just check this out. It turns out the derivative also has special units. And actually, this isn't something crazy. Just remember the fact that the units of the derivative are slope. The derivative fundamentally means slope. Let's go back and check this out. Derivative equals slope. So because the derivative is the same thing as slope, then the units of the derivative are the same thing as units of slope. So here, let's go back to this not clowns, little prognostication there. Let's go back to this back hair thing. If n of t is number of back hairs, and then t is in minutes, then the derivative has the units of slope, which is y over x, which is number of back hairs divided by minutes. And if you want to, you can write that as number of back hairs per minute. And so in this case, n prime of t, that's what this is read as right here, that dash is a prime. N prime of t really is a rate. It's a speed at which things are happening. Similar example, dudes. Let's say that we've got this thing where c of x is the number of clowns under your bed after you forget to bring your math teacher cookies x days in a row. It's horrifying, which is why you should always remember to bring your math teacher cookies. Now, if we look at c prime of x, it's going to have units of slope, and slope has units of y over x. Y, in this case, is, let's just shorten it and say number of clowns divided by, and your x units implicitly are days. So if you want to, you could rewrite this as number of clowns per day. And if you wanted a nice graphic to see what this horrible situation looks like, well, it looks like this. And this is exactly why I recommend bringing me cookies. All day, every day. So that's cool, dudes. And the general idea behind that is that the derivative, or f prime of x, has units of f units over x units, same thing as y over x, and same units as slope.